In the previous lecture, we discussed about the lossless power divider, and we saw that while the power divider, as the name suggests, is indeed lossless, it has a number of drawbacks. First of all, it is not matched at port 2 and 3, it is only matched at port 1. Secondly, between ports 2 and 3, there is no isolation. We discussed the requirement of isolation between ports 2 and 3, and we saw that ideally a power divider should offer isolation between ports 2 and 3. So, towards the end of that lecture, we also discussed that Wilkinson, an American scientist, made an important modification, an important but a simple modification to the lossless power divider, and what he essentially did was to add a resistor between ports 2 and 3. So what it essentially looks like is this. So the lossless power divider essentially looks like this. We will assume that the second conductor is ground. This is port 1, port 2 and port 3, and each of these line impedances of the arms are root 2 Z0, while the impedance of the port lines are Z0. This is the lossless power divider. So what Wilkinson did was to include a resistor between ports 2 and 3. Of course, the assumption is that the space consumed by the resistor is very small as compared to the wavelength of the wave that is flowing in the power divider or combiner for that matter. So what we discussed was that the analysis now becomes slightly tricky because there is this element, this resistor, which sort of creates a triangular connection. So therefore, whichever port you look at, the analysis sort of would not be so simple, because the impedance transformation is now something of a challenging task. So therefore, what we will now do is two things. We shall from this point assume that the bottom conductor is ground and we shall not show it. What we will essentially do is that we will look at this Wilkinson power divider from the top view only, and we will assume that the bottom ground conductor is there, it is implicit, but we will not show it in the diagram. So the top view looks something like this. Port 1, port 2 and port 3. And each of these lines, as we mentioned, are quarter wavelength long. Just like what was there in the lossless power divider. Now, to understand how to analyze this kind of circuits or this kind of RF networks, let us take a step back and go back to our knowledge of analyzing simple electrical circuits. Suppose I have a circuit which looks like this: a voltage source and two resistors. Let us say the voltage source is 10 volts and each of these resistors are of 4 ohms each. Now, let me define this voltage at this point as Vx. So, if I ask you to find out what Vx is, it's very easy. We can say that Vx is essentially 5 volts. This is very easy to say. But there is one more way, a little roundabout way to look at the same thing. And that roundabout way is what we will assume in our analysis of the Wilkinson. I can look at this 10 volt source as a series connection of two 5 volt sources. So let us say I have these two 4 ohm resistors as they are. And this 10 volt source, I will show it as two 5 volt sources. Whereas on the left hand side, what we are seeing is that there is a direct connection between these 2 points. There is no source over here. So a short circuit is essentially a 0 volt potential. So therefore, we can show this 0 volt by using two series sources. Let us say one of 5 volt and the other of minus 5 volts. So effectively what is happening, the meaning of the circuit does not change. This is another way to look at this circuit. So therefore, what we will now do is we will apply the superposition principle. That is, the superposition principle is something that we already know. So what we will first do, is that we will look at the two 5 volt sources on either side and deactivate the remaining sources. So step 1 is we will consider these two 5 volt sources. That is like saying I have a 5 volt over here, the two resistors, and another 5 volt over here. So the case where I am considering two exact same voltage sources, this is called as the even mode. Why? Because they are of the same polarity. So let us call this voltage now as Vxe, that is Vx in the even mode. I can very quickly analyze and say that Vx in the even mode is equal to 5 volts. I can very easily say that. At the same time, what about the current? Let us say this is some Ix in the even mode. I can say for sure that Ix will be 0. There is no current. It is like saying, because the current is 0 everywhere, but we are concerned only about this Vx point, it's like saying over here there is a virtual open circuit. This is what the even mode looks like. Now, let us look at the case where the remaining two 5 volts are activated. So on this side we have the minus 5 volt source, and on this side we have the remaining plus 5 volt source. And the two remaining sources which we had considered in the even mode are now deactivated. So therefore, let's call this voltage as Vxo in the odd mode. And the current, if any, let's call this as Ixo. So we can immediately say that because these two sources are opposing in nature, some current will definitely be there. But what is Vxo? Vxo will be 0. That means at this point, because the voltage is 0, it is like saying there is a virtual short circuit. There is a virtual short circuit at this point. And because I am applying superposition principle, I can say that the net Vx using superposition is Vx in the even mode plus Vx in the odd mode, and that is nothing but 5 plus 0, which is 5 volts. This is something that we can very easily do. Now, the other way to look at this is from an electromagnetic angle. Now, suppose we replace this circuit with two conductors, one over here and another over here, two identical conductors. If I now say that there is current flowing in these two conductors, equal current, let us say I and I, and the currents are time varying in nature. So then what will happen essentially is that there will be some magnetic field which is generated around these conductors. Same over here. So, as you know from the right hand thumb rule, if the current is this direction, the magnetic field will be in this direction. So, what will now happen at the center, or at the midpoint between the two conductors, the two magnetic fields will interact with each other, and because they are equal and opposing, because over here one field will look like this and the other will look like this, so the two magnetic fields will essentially cancel out. And what will happen is that the effective magnetic field at the center will be 0, which means that the net current between these two is 0. So therefore this is called as the even mode. If you notice, this even mode is very similar to the even mode which we saw in case of the simple circuit that we took, where we have two identical sources. And those two identical sources are now visualized in the form of two identical currents. Now, if I have the same two conductors, and on one side I have current I, and on the other side I have current minus I, then what will happen is that the magnetic field lines here would look like this. But over here, they would now change here and here. Now, because of these two opposing currents, if you were to look at the electric field variation between these two conductors at the midpoint, what would essentially happen is that the voltage or the electric field you would see a null over here. And if the electric field is 0, the potential would be 0, which is very similar to the odd mode that we observed in case of the virtual short circuit. You can think of this phenomenon like a capacitor, two plates of a capacitor which are charged with opposing voltages. So therefore, this is what is called as the odd mode. Now, using this even mode and odd mode, we can quite simply analyze circuits in two different modes and simply superimpose the two results and observe what the final behavior of the circuit or the network under question is. Well, having discussed this, let us apply this concept into the analysis of the Wilkinson power divider. So, what we will do, the first thing about the even and odd mode analysis is that we need to identify a line of symmetry where we can claim that the voltage or current would be 0 in the odd mode or the even mode respectively. So, if we look at the top view, if we now look at the top view of the Wilkinson, what we will do we can draw a line of symmetry over here. That is the only way with which we can divide this circuit into two equal halves. This is port 1, this is port 2, this is port 3. So what we can do, we are seeing that this line of symmetry is essentially passing through this resistor. So we can very easily represent this resistor as a series connection of two resistors, each of value R by 2. So therefore let's do this. This is what the line of symmetry looks like. Now suppose we are looking from port 1. We are looking at it from port 1. Let's not forget this is root 2 Z0. This is root 2 Z0. These lines have characteristic impedance of root 2 Z0. Suppose we are now looking from port 1. Suppose we are launching a wave from here. We expect that the wave will first get divided into two equal halves along this point. So therefore, what will essentially happen is that two identical waves will start flowing in this direction. So therefore, we can say the moment we have an input at port 1, this resembles the even mode because we have essentially two waves flowing in the same direction on the two conductors. So I can say input at port 1 is very much equivalent to an even mode. So what we can also do is that to make our analysis simple, we have to assign certain port terminations. For S parameter analysis, we know that each port must be terminated with some Z0. Another thing what we are seeing is that this line of symmetry will now also cut through this Z0. So what we can do is a simple modification where I can visualize this Z0 as a parallel combination of two resistors, each of value 2Z0. So let us redraw this circuit. So port 1 now will look like this. This is what it will look like. So now what happens essentially is that if we apply the even mode, this line of symmetry will bifurcate this circuit into two identical halves. And along this line of symmetry, a virtual open circuit will exist. In the even mode, what will happen is that each of these points will now get replaced by an open circuit. If I am drawing the top half only, so this R by 2 will see an open circuit. So these will not play any role. So the question is, looking into port 1, what is the impedance seen? The impedance seen is nothing but this Z0 transformed by this QWT quarter wave transformer of impedance root 2 Z0, and that is like saying it is Z0 square by Z0. 2Z0 square by Z0 which is 2Z0. And at the same time, the lower half is also seeing a resistor, this Z0 essentially getting transformed into 2Z0. Thereby, when you are combining the two, the impedance that you are seeing is essentially Z0. What about in the odd mode? In the odd mode, this line of symmetry will be replaced by a short circuit. So therefore, what it will look like is this. If I am drawing the top half, this side will essentially be a short circuit. And over here also, this R by 2 will see a short circuit. So effectively, the Z in 1 now seen from port 1 will be 0 because this short circuit will dominate. So in the even mode, the resistance or the impedance seen from each of the top and bottom half will be 2Z0, which makes the net impedance in parallel as Z0, and in the odd mode it will see 0. So therefore, the net impedance that port 1 sees is still Z0 as per the superposition principle. So therefore, port 1 is matched, just like what was the case for a lossless power divider. Now, let us look at ports 2 and 3. Let's look at port 2. Let's look at port 2. So in the even mode, or let us say, forget the even mode, let us say we give some input at port 2. Let us give some voltage source over here, let's call it as Vs. So it's like saying, I'm having this power divider where port 1 is terminated with Z0. This is R. Port 3 is terminated with Z0, and here I have the Z0 impedance and I am putting this voltage Vs as an input at port 2. We now have to see how to analyze this. So therefore, let us again divide this as a line of symmetry. So in the even mode, we will first see this 2Z0 because Z0 can be represented in parallel as a parallel combination of two Z0 resistors, two of them. So here there will be an open circuit, then this line, then we will have this R by 2, then open circuit, then I think there is a little bit of a issue. Let us look at this in a little different way. So let us apply the even and odd mode analysis in a bit of a different way, just the way we had done for the simple circuit. So let us first draw the parallel combination of these 2Z0 twice. This is port 1. Let us show this resistor again as two R by 2s. This is Z0. There will be this Vs. What is interesting to see is that there is no input at port 3. So just like what we did for the analysis of our circuit earlier, we can assume that Vs is essentially a series connection of two sources, each of Vs by 2. So let us say, I'm showing this Vs by 2 and Vs by 2. And since there is no source over here, we can represent it as two series connections of Vs by 2 and minus Vs by 2. This we can do. And then what we can do is we can draw a line of symmetry. Let me repeat. The input voltage at port 2 is Vs and the input voltage at port 3 is 0. So to make it look like a symmetric circuit, we will apply the even-odd technique similar to what we had done for that simple circuit towards the beginning of this lecture. And we will show the 0-volt input at port 3 as two voltages of opposing polarities, Vs by 2 and minus Vs by 2. Now, in the even mode, we can consider this Vs by 2 and this Vs by 2. So therefore, this one would behave like an open circuit. So therefore, port 1 will have this 2Z0 and this one will look like an open circuit, and then this followed by Z0. There will be an R by 2 and a Vs by 2 over here because we are considering each. So this is the top half. So what can we do with this? So when we are now looking from port 2, let's call it at Z in 2 in the even mode. What is the impedance that is seen? This is a quarter wave transformer and the line characteristic impedance is root 2Z0. So Z in 2 in the even mode will be this 2Z0 transformed along this, and R by 2 will not play any role whatsoever. So therefore I can say this is nothing but 2Z0 square divided by 2Z0, and this is equal to Z0. So in the even mode, port 2 is perfectly matched. But is that enough? No. We have to ensure that in the odd mode also, the port 2 is perfectly matched. Only then we can say by superposition that port 2 will be always matched. So therefore, let us look at the odd mode. Plus Vs by 2 in port 2 and minus Vs by 2 in port 3. So therefore, all these open circuits will now be replaced by short circuits. Vs by 2. So again, this is a quarter wave transformer of impedance root 2Z0. So the impedance at port 1 now will be 0 because of the short circuit. and short circuit transformed by lambda by 4 will be an open circuit. So now Zin looking at port 2 in the odd mode will be this R by 2 in parallel with the transformed impedance from here, which is an open circuit. So therefore this will be R by 2. Now what we want is that port 2 should be matched to Z0 in even mode as well as odd mode. We saw that even mode it's working, but odd mode the impedance seen by port 2 is in terms of R, and what we want is this should be equal to Z0. So that means if the value of R is 2Z0, then port 2 will be matched. Perfectly matched in the odd mode, but for this condition. This is very important. So now we know that the value of this resistor, which has to be placed between ports 2 and 3, must have the value of 2Z0, because for that R by 2 then can be Z0, and therefore it can help port 2 to be matched. So this analysis is now becoming very interesting. This analysis is now becoming very interesting. Why? Because earlier, in case of the lossless power divider, ports 2 and 3 were not matched. Now we are seeing by putting this resistor R between ports 2 and 3, effectively we are making or giving a provision for port 2 to be matched. Likewise, just like the way how we proved that port 2 is matched in both even and odd modes, the analysis for port 3 will be identical, because ports 2 and 3 are very much symmetric. So therefore, putting this resistor between ports 2 and 3 will ensure that ports 2 and 3 are matched, and even port 1 is now matched. We have already verified that. Because when you are looking into port 1, this resistor does not play any role, because it is behaving like an open circuit in the even mode. So we have taken the lossless power divider and we have shown that if you introduce a resistor between ports 2 and 3 and keep the value of this resistor as 2Z0, then you can make ports 2 and 3 matched also. So therefore, we now have a technique to match ports 2 and 3 also. Next, we are not done yet. So far what have we proved? We have proved that all ports are matched. But we have to ensure that the transmission coefficients must not change from the values that they were in case of the lossless power divider. So now, because all ports are matched, I can say that S11 will equal to S22 equal to S33, and that will be 0. Now what about S21? In case of S21, what will happen? Let us say I am putting a source over here, Vs at port 1, Z0, this is port 1, this is port 2, this is port 3. This is root 2 Z0 and length lambda by 4. Now, if I am getting an input over here at port 1, what will be S21 and S31? Well, I can say if the input is at port 1, again there will be two identical waves flowing along these two lines. So therefore this is like saying it is the even mode. So therefore this resistor will not play any role whatsoever. And I can say that then this circuit will look exactly like what is the case for a lossless power divider. So therefore, for input at port 1, R plays no role. So it is just like lossless power divider case. It is just like lossless power divider case. So in that case, what we saw was that S21 is equal to S31, and that is equal to minus J by root 2. So therefore, this still persists. This one still persists. Now, what about S12 and S13? What about S12 and S13? Well, in the even mode, if you apply the same input at port 2, let us say there is Vs by 2 at port 2. So in the even mode, what would happen is that it will have Z0. This resistor won't play any role. This is open circuit, R by 2. There is an open circuit over here, and there will be a 2Z0 in case of port 1. So if you analyze this, taking 2Z0 as the load, so this is lambda by 4. Let us say this is L equal to 0 and this is L equal to lambda by 4. You can again follow the same approach using the transmission line voltage and current to find out the voltage over here. We can do that. So while doing that, you will see that the result would essentially be the same as what we had derived in the previous case for the lossless power divider. For that case, we had applied the input over here and checked the output at port 2. But by applying the input over here and checking the output at port 2, you will see that even S12 is exactly the same as S21, and that is minus J by root 2. Now what about the odd mode? Even mode is this. So in case of the odd mode, we are assuming Vs by 2 over here, and port 3 has a minus Vs by 2. Now there will be a short circuit here and a short circuit here, and this 2Z0 will also be terminated here. Now because of this short circuit, no power will go here, and if R by 2 is equal to Z0, then all the power from port 2 that is reaching, all the power from this source that is reaching port 2 would be dissipated over here. Nothing will go here because of the match load. Sorry, because of the short circuit. And because R by 2 is equal to Z0, it is matched. So there is no question of any power going anywhere else, because this short circuit looks like an open circuit over here because of the lambda by 4. So that means in the odd mode, when there is an input at port 2, no power reaches port 1 and obviously no power reaches port 3. All the power is dissipated over here. So in this case, S12 is 0. So that means combining even and odd modes, I can say that S12 is equal to S13 and that is equal to minus J by root 2. Now, if you recall, there was one more problem with the lossless power divider, and that was that it suffers from low isolation between ports 2 and 3. So what will essentially happen in this case is, if I give any input at port 2, whether it is the even mode or the odd mode, absolutely no power will reach port 3, because in the even mode, this will look like an open circuit. So therefore there is no interaction possible between ports 2 and 3. The open circuit will isolate that. And in the odd mode, thanks to this resistor, all the power that is coming from this source at port 2 will get dissipated. So therefore, whether it is the even mode or the odd mode, any input at port 2 will not reach port 3. And furthermore, any input at port 3 will never reach port 2. So that means S23 is equal to S32 is equal to 0. That means perfect isolation. Now all this seems very convenient, right? And it is. But the problem is, there is a problem. The catch over here is that because of the resistor that is between ports 2 and 3, it is ensuring that the power division and combination are taking place with this 1 by root 2 ratio, just like the lossless power divider. But the loss introduced by this resistor over here between ports 2 and 3 is used to ensure that there is no communication at all between ports 2 and 3. So therefore this is ensured by the resistor R, and that is equal to 2Z0. So what this means is, we are actually introducing some loss, and we are using the loss in a good way. We are using the loss in a place where we need the loss, where we need that no power must be transmitted from one point to another point. This is a good way to keep ports 2 and 3 isolated. At the same time, it is ensuring that as far as the communication between ports 1 and 2 or 1 and 3 is concerned, there is no change. It behaves exactly like a lossless power divider or a combiner, but the loss, because of the resistor that is introduced between ports 2 and 3, is used in a very clever way to maintain the isolation between ports 2 and 3. In other words, there is absolutely no communication of any signal between ports 2 and 3. So this was a very big landmark achievement by Wilkinson, and this power divider and combiner is being used in this day and age also because of its simplicity and versatility. We shall continue from this point onwards in the next lecture. Thank you.